Okay, so I'm gonna get started. You might hear me, stutter a little bit when I'm letting more people coming on in, but let's go ahead and get this boat on the road. Today, we are hosting a colloidal silica course through our Colloidal Silica and Concrete Association. I want to welcome everybody to our inaugural presentation, and I wanted to surprise all of our 19 people who showed up. Each of you is getting a free t-shirt from CSCA. So please make sure to contact Patchouli so she can get in shipping information so we can send everybody t-shirts. I'm really excited for that. Today we're going to be going over colloidal silica for concrete, specifically how to tell the difference between or whether or not it's the savior, it's going to be a tool in your toolbox, or it's a snake oil. And joining me today is the president and CEO of Intelligent Concrete, Whitney Lee Bitter-Belkowitz, and from RL McCoy, Dan McCoy. And of course, my name is John Belkowitz. And just so everybody knows my role in all of this, I am the inaugural president of Ali. How you doing, sir? I am the inaugural president of the Colloidal Silica and Concrete Association, and our overall mission is to bring consensus-based knowledge to a larger concrete and construction industry to ultimately give you another tool in the toolbox. And this is the format of the presentation. Like I said, we really didn't want this portion of the presentation to go over 20 to 30 minutes. So I'm going to give my laboratory spiel, and then Dan is going to go into his field spiel. We're going to go from the labcrete to the bookcrete, and then we're going to open up the floor for any questions. Okay, so Whitney and I have been working with nanosilica, colloidal silica, and concrete for the better part of 2 decades now. Dan, I think you've got 3 years of experience, 2.5 years of experience in it. Dan will give you his intro here in a second. We started the Colloidal Silica and Concrete Association as a way to disseminate this information about this tool in the toolbox to a larger concrete construction industry. And we wanted to do this in a way that not only highlighted the bookcrete, but the labcrete and the realcrete. And ultimately, that's what we were going after. The research motivation behind all of this was we have over 600,000 concrete bridges in our national inventory, establishing this $48 billion a year industry. You know, of that, an additional $8.3 billion is put back into concrete every year to deal with the maintenance associated with physical and chemical attack. What we found is that nanosilica can be a solution to a lot of the problems that we have out there, and to include, you know, our constant issue out here in the Western US business unit with alkali silica reactivity. We've also found a lot of great potential for calcium oxychloride formation. With all that being said, a lot of people are asking, what is colloidal silica, and how can we tell the difference between colloidal silica and a very expensive salt water? So that's the first thing that I wanted to talk to y'all about today. Dan is going to be talking about, once you find the colloidal silica that is the real deal, then how do you determine that it's the right colloidal silica for your end means? And Dan's going to go through with you how he did it. Is that a fair assessment, Dan? Uh-oh. Did I mute you again, Dan? That was not intentional. Oh, for the love of Pete. There it is. There you go, bud.
I'm here. Yes, I am here. I should be going through that. Hopefully, I'll be able to give everybody a brief story of how it came to be, and then how we were able to advance the participation of local municipalities and the DOT, and how, you know, to the buzzword synergy, and then RD&D came into effect for research development and then deployment. Anybody else in other markets out there, it's kind of a really good story of how to get involved and how to start something. And hopefully in Northeast Indiana here, we've paved the way, and now it's getting broader to the things that you need to know. So yes, that was an excellent introduction.
I think that was an excellent pun where you said paving the way. That was awesome.
I didn't even catch it.
Oh my goodness, I caught it. So talking about paving the way, to pave the way for this presentation, I thought that a little bit of a definition was warranted. And if you've never seen colloidal silica up close, here it is. This is a classic picture from Brian Green's work back in 2008. And it looks like basically like a milk. And that milk is a liquid dispersion of nanosilica particles that can have anywhere, or a diameter anywhere between 1 and 100 nanometers. Like I said, it's a liquid dispersion, clear to milky depending on particle size. And compared to silica fume and class F fly ash, it's going to have a bit of a higher purity, but much higher surface area. And again, it is a liquid dispersion with solids content that can vary. And when we put it under the microscope, we are still looking at a ball bearing compared to our class of fly ash or silica fume. But again, we're looking at something that's 1,000 times smaller. And if you don't know what a nanoparticle is, just to give you a reference, hair on your head is around 100, 150,000 nanometers in diameter. Our nanosilica particles anywhere between 1 to 100 nanometers in diameter. Okay, and what we see out of nanosilica is just like with the class of fly ash and the silica fume, we have that pozzolanic reaction, the promotion of the calcium silicate hydrate, that superhero of concrete strength, to be produced out of the expense of calcium hydroxide. We also see particle-to-particle packing, ultimately creating an environment that is not conducive to chemical or physical attack. And we see it increasing the strength and durability. And the difference being with a nanoparticle, it has more free surface area for that instantaneous pozzolanic reaction. We also see this accelerated cement dissolution and more hydrates growing because of that nanoparticle size. Now, for years, I've been working with different nanoparticle products out there. I have my favorites, and Dan's going to be talking about some of the stuff that he's been using, which, you know, my favorite out there. But we've used a lot of stuff that claim to be nanosilica or colloidal silica, nanosilica in a colloidal suspension. And it turned out to be very expensive salt water. So what I wanted to do was use my time to talk about some of the ways that you can either do it in your own laboratory, or if you don't have a laboratory, you can hire a third party, and there's a whole bunch of them on the internet that you can reach out to. A lot of the classic ones can do these tests. They're very easy tests. But the first thing that you can look at when playing with colloidal silica and identifying, is this really a colloidal silica, is doing a quick pH test. Now, you know, you can always use litmus paper out there that's available. But, you know, you can always go on to Fisher Scientific or Amazon or Ted Pella and get yourself a fairly good pH probe. And what you want to look for is the pH of the solution. If the pH of your colloidal silica is above 11.3, there's a good chance that it's not truly colloidal silica, and more than likely it's a silicate. Now, another step, and again, some people have these tests in their labs and some people don't, but another way you can look at this is looking at the specific surface area. Now, when we're talking about colloidal silica, we are talking about a dispersion of nanosilica sized particles. So because of that, there is a range of particle size distribution. And because there is a range of particle size distribution, there's a certain surface area that we should be able to measure using the Sears method. And that range is somewhere between, that specific surface area, somewhere between 30 meters squared to 2,700 meters squared per gram. Anything higher than that or outside of that is either way too small to be a nanosilica, or it's way too big to be a nanosilica. All right. You know, and where this is all coming from, I'm very fortunate to be part of a group of wonderful, wonderful people we are all working together to put a new ASTM together for colloidal silica and concrete. And one of the main objectives is to make sure that what we have here is actually colloidal silica. The other objective is to identify that what you bought is what you received. And part of that is a uniformity confirmation between the certificate analysis from the manufacturer and from the distributor, from the distributor. And with that, we're doing some very, very basic tests for that uniformity to include strength activity index, mortar flow test, solids content, specific gravity. And ultimately, those should match up to that certificate analysis to ensure that what you bought is what you got. Now, these are very, very basic tests. They're very easy either to kick off or have a local lab run these tests for you. And as I see on the list, we've got a lot of folks on the phone who have either run these tests, can run these tests, or help create a lot of the protocol that I'm talking about right now. Okay, so now I wanted to hand this off to Dan. Dan, please take her away. And Dan, just let you know, that job site that we were talking about in Eagle, Colorado, here's a picture of it if you wanted to use that.
Oh, perfect. Yeah, that's fantastic. So as Dr. John had mentioned, 2.5 years ago, well, 3 years ago, NDOT came to us. Now, a brief background on my history. I'm a third generation bridge builder, a second generation concrete pumper, and a first generation engineer. So pretty much all of my life, I've been doing things like this. And I was always interested in new technologies and new methods. And the Indiana Department of Transportation came to us on a contract. I'd heard about this product E5 through our pumping world from different people. Hey, is it okay to pump? Is it this? And I said, well, I really don't know. You can try it and see how it goes. And that was done on commercial and residential jobs quite a bit. And this is the E5 internal cure portion of the nanosilica. And they came to us and said, listen, we want to try, and this was Mike Nelson, so the concrete materials engineer for Indiana Department of Transportation. He said, we want to try eliminating wet cure on our bridge decks. So in Indiana, we have a 7-day wet cure. We don't have that anymore because of E5 internal cure. And one of the things that we didn't know was, how is this going to affect all this stuff? The pumping, the finishing, the curing, the strength. How is this going to work? And fast forward, it's all been wonderful. Like I said, I've been trying, I'm an engineer. I look for holes in things, and I've been trying to find negatives. And I can't find any as of yet. Of course, it's susceptible to any abuse that is over abuse, as any concrete is. But what we did on those first 2 bridge pours was frankly quite amazing. It was the first time that we had used that in a transportation application and eliminated wet cure. And the strengths turned out better than normal, indicating that it really was helping with the hydration in it, and it was not allowing that excessive evaporation to take place. And you could see that physically on the concrete surface by the lack of bleed water that you would normally see. So something was happening there. It was holding on to that water and yielding it then later to hydration. So that's the good stuff that we're looking for in engineering. And we went from there, and we had problems in Indiana, and I think there are problems pretty much nationwide in the colder regions, the northern regions, where of course temperature becomes a concern. But over the longevity and lifetime of a structure, we had a lot of problems with overlays. So bridge deck overlays. So we're talking, if the rest of you were in this, like in a parking garage, you'd consider this a topping slab, I guess. But, it's basically a dense wearing surface that we wanted to put on to protect the structural integrity of the slab underneath it and allow traffic, plows, chloride intrusion, all that stuff. We wanted to limit that. So we were having a lot of problems with plastic shrinkage and shrinkage cracking. Well, it turned out that inherently it was the mix that really was the problem when we started looking at it. We started off, you could either do a 658 pound type 1 cement with an acid, and then also with a an epoxy, which is like a modified overlay. So an epoxy overlay, which that's great. That still required 24 hours of cure. It had really good bond values. The problem was you only could do that out of volumetric mixer trucks. So it wasn't on demand to ready mix. So it kind of limited you on your location and your schedule, because there were only so many providers and suppliers that would be able to produce that. And then you have on-site storage of your materials that you had to do. And so it was kind of logistically difficult. So the other option that they came up with about 4 years ago, and they had quit this for the longest time, was the silica fume overlay, the what we call the micro overlay. And they would use silica fume as a 7% addition to the 658 pound mix. So I mean, if you're doing your math, that's about 708 pounds of cementitious in this mix for overlays. And then, as we learned later, even though we were trying to go for lower water cement ratios to maximize compressive strength, what we ended up realizing through SEM analysis and other lab work was we were starving the cement particles. So we had a lot of unhydrated cement particles in there, and they just essentially, as Mike Nelson put it, we've got a lot of really expensive fine aggregate because it was not hydrating and producing any value in terms of cementitious to the concrete mix. And with that, we had a considerable problem with plastic shrinkage. If you think about a bridge, we have no control joints in a normal structure unless there are joints placed specifically at negative moments over piers, or if it's designed in single span scenarios over multi-spans. So most of them are continuous spans. And when you think about it, it's a long bar. It's only 30 feet wide, 40 feet wide, and then 2, 3, 4, 600 feet long. So that shrinkage starts to happen, and you see cracking in the transverse direction. So what was the solution for that? And this is where it gets into trying new things. We had the go-ahead from NDOT for the E5 internal cure, and then Specification Products came out with another product that was called liquid fly ash, which Dr. John can get into it a little more, but in layman's terms, for me as an engineer, I just thought of it as the internal cure is more like a stone, and then the liquid fly ash is more like a gravel in a super fine type of element. So you've got the internal cure, which is pretty much a uniform nanoparticle, and then you've got the liquid fly ash, which has got a bunch of different nanoparticle sizes in it. And so you've got all these surface areas causing pozzolanic reactivity. So that gave us, if we wanted to keep our specification for strength about to the same, equal, I think, I'll get into this later, but there's some research that says, how strong do we really need our concrete? When do we have to start worrying about brittleness? So in the transportation world, we need to be more concerned about structure longevity, durability, and resiliency put up to harsh conditions, not so much large impact loads or large compressive loads. So more or less being out in the elements. So if we thought if we can halt or limit or reduce the cracking, then we're going to win half the battle when it comes to lifetime longevity, because those chlorides get in there, you begin popping, freeze thaw it just gets messy several years down the road. And you have overlays that look pretty patched and pot worked after 15 years when, they're scheduled for replacement at 25 years. It's what you try to get out of them to extend the lifetime of the structure. So we had this LFA, and we were lucky enough that we had an overlay at a county, on the county level. So dealing with county, so starting with small municipalities. And we went to them and went through the research, and we went to the county engineer and said, look, I think this is the solution we're looking for an overlay to limit the problems that we've been having with previous overlays. And we tried it. He was gracious enough to let us try it. And that's Brandon Forrester, the county engineer for the Whitley County Highway Department. So it's the big things that were done in smaller ways to precipitate these changes. And we tried that with the liquid fly ash. So we ran a 580 cementitious. So we've dropped it from 658 to 580. We actually increased the water cement ratio, but we still, when compared to a like mix of an overlay, we still had less water per cubic yard in that concrete. So that was less shrinkage potential we had, right? We've got less paste in there, so we've got less shrinkage potential. And with that liquid fly ash, it allowed for that extra pozzolanic reactivity, as an SCM, to maintain basically the same type of performance we were getting with the 7-bag mixes. So, and once again, I went out on my own, and we did this without wet cure. We did it without a cure compound. So we basically put it down, used our bridge finish machine, strike it off, and then we surface textured it with as a tine, a typical roadway application, and we had very good luck with that. Since then, after that was done and we had really good luck, and we went over that deck several times, I'd stop there several times a month just to make sure that we didn't have any long-term issues. And it's still a great looking overlay, and there are no cracks related to the material at all for the surface. So that was a win. And once we started to stack up these wins, then the ready mix company we were working with was also trying it with other mixes in the commercial world that weren't very high risk mixes, because we said, okay, if this is a new product, let's start off with mixes that aren't, we're not going to try and put this in a hospital on our first try. Let's start off with, and one of the first ones was actually a hog barn. And when you think about it, you think, well, that's no big deal. It's just a hog barn. But if you guys, I'm assuming most of you guys are lab guys and engineers, and you really start thinking about the loading and the conditions that go on in a hog barn. You've got silage storage. You've got manure. It's getting cleaned out every day. It's getting cleaned out with chemicals every day. Very caustic environment. And that's when we went, this is going to be a perfect test run to see what these nanosilicas are able to do for the surface and the surrounding edges where we've got the existing wall was not used with nanosilicas, and it butted up right against. So we'll have a really good idea where to track, and that's about 2 years old. So from that and all that good information, we also had a bonus in the area of the US 30 coalition. And I'm in Fort Wayne, and there's US 30 that runs from Fort Wayne to Chicago. It's a major trucking route. It is not of a freeway type design. So wait times are extended because there's lots of stopping and starting. There's a lot of queuing, and they started this coalition several years ago to say, we want to turn this into a freeway. So that gave us something to aim at for a new technology that said, hey, if we're really going for durability and we need a place to try it, such as in paving, this is what we want to do. And this is what we're working our research towards. And then through that, we kind of came up with, I would just simply ask, local municipalities that I had jobs with, or some that had jobs that I already had relations with, to say, hey, let me try this. And oh, by the way, NDOT's very interested in it. And that got a lot of attention from the local municipalities to say, well, most of our specs follow the Department of Transportation. So if they're involved, we feel really good about it. And Mike Nelson was more than gracious to participate in via emails and via phone calls. We had some with the DOT and with Federal Highway to say, look, this is what we're doing and this is what we're trying. And they gave us the plain go ahead to say, hey, it's the state's rights. You're entitled to your experimentation. So, and that's what we started doing. So we started putting it in other transportation infrastructure products. Now, the one thing that's really neat about infrastructure is, and especially what I think is really neat about E5, the internal cure, and the liquid fly ash, is that even though the transportation market does not control the volume of concrete produced, they have the most stringent demands on the material, both from the laboratory, the specification, and the use. So if you can get something through a transportation department and try it in transportation, you find that local commercial jobs look at it and go, well, if it's good enough for the DOT, it's probably going to be good enough for a parking lot. And that's how it kind of rolls downhill and gains attraction. But it's as Dr. John said, to get to the point of the video or the presentation that is real versus fake. I think what is important to know is to compare to everybody. And this is why the ASTM standard, I think it's, John, you can correct me, but I think it's 6809 or something, but it's basically going to say, this is what you're getting when you order. So to compare for the rest of, so everybody else, when somebody says a nanosilica or somebody says a colloidal silica, think to yourself, we're a bunch of contractors anyway, but think to yourself beer. All right. If somebody says, I'll have a beer, there's a lot of different beers out there. And everybody has their own defined taste. And there is a right beer for the right person and the right application. It is the same way with this technology. We found the right nanosilica, and the guys at Specification Products had the right development and the right testing done, and they're still continuing testing. They're trying to find holes in it that even I haven't thought about. And, everything is coming back positive. Every little thing that I hear, it's just like, wow, it's doing more than what we thought. And that's great. That's fantastic. But it is a very specific concentration of nanosilicas, a very specific size, very specific pH, very specific particle charge that goes through the manufacturing process. So this is a manufactured product that is essentially very tight in specifications with what they put out as a final product. So what we found was the differences that we saw were usually in the cement and the aggregate and the water used, because we knew that the internal cure, the nanosilica and the liquid fly ash nanosilica, were going to be the same. They don't change. But depending on what cement you had coming out, and so for the QC guys that are on the call that deal in larger applications for ready mix, that's what you pay attention to, is what is your cement source, do some trial batches, and then, pick some mass placement. Because what we found was that when we got this mix into the field and started doing hundreds and thousands of yards with it, man, it blew lab results out of the water as far as what we were doing. And I know that one of the things that is very important when we're talking about environmental, one of the things that we try to do, I did it selfishly as an engineer to say, I want to reduce shrinkage because I want to extend structure life. Well, all that is good for the environment, because the less I work on a structure over a certain amount of time, the better it is for the environment, the less wasted materials, and the less water usage, the less overall, the less overall material usage you have. All of that is going to be beneficial in the end when you're talking colloidal silica usage and where we're eventually going to try and go. So I think, Dr. John, did I answer most of your questions, or does that give everybody a good idea of how to proceed with, do you think that gives everybody a good idea of how to proceed with introducing it to their market if they want to try it? And I think we're all open for suggestions if anybody does have any questions in their markets as they propose these to people. I know I've talked to Ohio several times just with the experience we've had. So if you think that's good.
I think that's great. No. And that's what I wanted you to do. I wanted you to talk about the process where you decided to use the low risk, and then you got riskier as time went on. It wasn't just you. I'm using the royal term of the you.
Yeah.
I want to open up the floor for any questions. And the way I was hoping that this was going to be wrapped up in a bow is that the way we presented this to you is that colloidal silica is another tool in your toolbox. With aggregate changing, with fly ash changing, dare I say, even what we were used to vanishing almost overnight for some folks, we need a solution. And getting Class F fly ash from Mexico or from, Chechnya, it to me is not an economical and viable solution. So, I mean, that's how we wanted to propose or to present this information. And I think Dan had said it, challenge us. If you don't think it's going to work, shoot. When I first used the colloidal silica, I didn't think it was going to work 20 years ago. I mean, come to my surprise, it's one of the most awesome technologies in the flipping world. And that's why I've dedicated almost 2 decades to it. But we've got great people who've done some great work. And at this point, I'd love to answer, and I'm sure Dan would too, any questions that y'all have. And if you don't have questions, for those of you who are staying on the line, I've already got some questions that I prepared just in case, but we've got the chat open, and let's go. Let's ask some questions, folks. I'll give it about 10 seconds and I'll present my first question. So one of the questions that I run into is, how does colloidal silica impact the concrete mix design specific to the fresh properties? Dan, I was going to take this one and then maybe about a minute or so and then hand it off to you, if that's all right.
Mm-hmm.
So one of the things that we found, and this was a lovely project done by the folks at University of Wisconsin, is that colloidal silica has a tendency of increasing the efficiency of a lot of other admixtures. And in our case, we were doing this job site out in Eagle County Airport. This was back in 2011, 2012 timeframe. Very standard pavement mix. I think we've got it in kilograms per cubic meter. And we found that when using the colloidal silica, a very small amount, we could reduce our high range water reducer content and still maintain not only our slump, but we also increase the slump life. Dan, did you want to take it from there?
Well, one of the main things that I saw the benefit in the field, first and foremost, as a concrete pumper, was even though specification products does not claim it to be a viscosity modifying admixture because it's not labeled that as such, it certainly acts like it. So we saw reduced pumping pressures of almost 100 bar on average between like mixes and then a mix with the internal cure mechanism of the E5. So that lets, and as you know, when you're pumping, it's that creaminess or the cement paste. So usually the higher the cement paste goes, the more a pump likes it. That's why it's so easy for a grout with without a lot of large aggregate to be pumped. So that is one of the things that I was concerned about environmentally, because if cement and designs were going to go down as a consequence of, and I mean down in quantity, as a consequence of greenhouse gas emissions, then the greener the concrete was going to get, inevitably it meant less paste for us, which meant harder pumping. But with internal cure, when you see that reduction, then it leaves that reduction in pumping pressure. It leaves that room to reduce your cement content a little bit without sacrificing either performance or workability in terms of pumping. And the workability flows right down the line to placement. I think Mike Nelson was absolutely ecstatic when we placed that first deck. And I told him, I said, I think this is the first and only bridge deck in Indiana that's never had a drop of water on it while it was finished. Nobody, we that first time we did not allow anybody to put any water on it. So we used basically a finishing aid. I believe another one, I think it's Miracle Aid is the name of it. That's another specification product. And I went with that, and I like that because it was the same nanotechnology for use as a finish aid. So they were designed to be used together, and that's why I liked it. You can use other finishing aids if you want, but you want to get away from evaporation retarders, which is what was assumed before to be okay. But a lot of guys in the field will then use the evaporation retarder as a finishing aid. And you don't, as Dr. John will say, he's probably cringing right now, you don't want to do that.
Yeah.
That's a lot of bad stuff for the surface of your concrete. So that was one good thing. I think out of all these bridge decks that we've poured, and wow, I've lost track now, it's got to be well over 50.
67, I believe.
In the state of Indiana.
Right.
And none of them have had a drop of water on it. So when you can change the culture of how we finish concrete and introduce good practices back into it, you're already winning the battle for the durability and the longevity of the structure.
All right, we've got some other questions here. One question from Evan, and Paul will get to your question. Evan said that we've been doing ASR at 1567, which is the accelerated mortar bar test with the LFA, and haven't seen positive results. Any suggestions? Evan, it all depends on, the reactivity of your aggregate. And, the first question is the 1567 appropriate? Here in Colorado, we use the accelerated mortar bar test. We don't use the 1293, nor do we go to Treat Island, and we have no problem using it. There are other places where the aggregate it's not the right test. So that's the first question. The second question is, depending on the reactivity of your aggregate, and as Dan had mentioned earlier, the type of cementitious that you're using, you're going to need different amount and different types of colloidal silica. And specification products, they have a number of products that can answer a lot of problems, to include ASR. And I think the best analogy, Dan used the beer analogy. I'm going to use a different analogy. Not that I didn't like the beer analogy, good analogy, but when I first got into the commercial industry, it was back in 2005. And what I mean by that is a formulator, as an engineer. So I used to work as, as a contractor, as mucker's apprentice, but after the military, got into the job working the commercial industry. We were just starting to use something called a polycarboxylate style high range water reducer. And oh gosh, this was the touted most amazing stuff. And the way we used it, we would, and when I say we, I'm using the royal term, the ready mix provider I worked with, they literally closed their eyes and threw the technology into the back of the truck. And when it didn't work, complained, why didn't it work? And though we did use it blindly for a time, we started getting more into it. We found that based off, you had to use different types of polycarboxylate based on the soluble alkali and sulfate content of your cement chemistry, that there was not a one size fits all high range water reducer. Now, I want to create the analogy between high range water reducers and colloidal silica. There's, very specific type you want to use. It's not as, it's a bigger barn door than high range water reducers. There are more one size fits all. That being said, if that colloidal silica isn't working for you, that might mean that there's an issue with the synergy between the colloidal silica, the nanosilica sized particles, and the cement chemistry. Now, what that means is we just need to figure out which one is the right one. And again, that's similar to the high range water reducer stuff that we had to do back in the early 2000s. And now, of course, we all know how to use high range water reducers based on changing cement chemistry. So it's not a big deal. We're going through that same process now. Hopefully I answered your question there, Evan. There was a question for you, Dan. I just want to answer this one question from Paul. Have you done any work with 1L cements? If so, have you seen any difference? Right now, we're doing a bunch of work with type 1L cements. And as I was just stating with Evan, yes, there are changes, but not significant enough for us to stop moving forward. And we are adopting and adapting to those changes happening throughout the entire US. And then, Dan, this question is for you. What is the average thickness of the overlay?
So in Indiana, it's an 1.75 inch minimum to about 3 inches by the time you mill it out, and then it slopes up. So, but why that's important to everybody is that's a huge amount of surface area for not a lot of volume. So that's why it was so important for the internal cure. Why I was so impressed. And then afterwards, we take a rake through it and we give it texture for the tining, which I think Dr. John had in one of his slides there that showed an airport taxiway, for the type of surface treatment that was given. So you look at that there's a lot of surface area there. So when you think about thermodynamics, there's a lot. It's just like a radiator. There's a lot of potential evaporation that could happen there. We're begging it to evaporate. And there was no bleeding in there, and we held it all in, and there was no plastic. Well, I'm sure there were plastic shrinkage, but there was no plastic shrinkage cracking. So that you could see. Now, the more I learn about everything in concrete is that, cracking happens and micro cracks exist. But if we can limit those canyons to a chloride particle or a water particle, that's what we're going for. So that's why I thought the overlay was very impressive, because we had a very small amount of volume and a huge amount of surface area that would invite evaporation. We've done it in several bad conditions. Some evaporation rates that were up around 0.37. I mean, it's just bad. I shouldn't have done it, but we did it and it worked. Mike Nelson looked at me and he said, if you make this work, you're going to make a believer out of me. And I went, oh my God, I hope it works.
And that was with no curing compound, right?
Correct.
Right. Now, hey, there's another question here for you, Dan. With the reduction in the amount of cement in a mix, what happens with the concrete's finishability, particularly on commercial or industrial flooring? Is the loss of fine paste only made up with fine aggregate? If so, a finisher is able to maintain the hard trowel surface. Hey, Joe, if you're available, I wouldn't mind if you jumped on to answer that one. No problem, Evan. Oh gosh, there you go. Joe, I don't know. Patchouli, you're going to be taking the controls next time. So Joe, if you don't mind talking about some of the warehouse floors that you worked on and that Chaplin abrasion test and how the finishing was.
I caught a little bit of that question, Dr. John. Can you re-ask it? It was
yes, sir. With the reduction in the amount of cement in a mix, what happens with its finishability, particularly on commercial or industrial flooring? Is the loss of fine paste only made up with fine aggregate? And if so, are the finishers able to maintain the hard trowel surface without fighting presumable coarser paste that comes along with the mix with lower cement levels?
Yes, we've done well over 12 million square foot of this reduction of cement with E5 LFA. And we find that the finishers find it more workable, and they see a spike in their FFFL increase because they don't have to hit it as much, and they can wait just a tad bit longer to get the machines onto the concrete because the concrete is setting from the bottom up to the surface. So I understand what the question is. By the reduction of the cement paste, you think your finishability is not going to be there. But the nanosilicas act like a ball bearing. They allow for that water, that surfactant, to be at the surface and interlock around the cement particle to allow that surface tension to break easier. And it allows the finisher to work the machine more efficient with the surfactant of the water instead of over trialing because there's too much paste. They start to corn roll it. So when you get too much fines, too much paste at the surface of the concrete, finishers want to seem to over roll it, get on it too early and cause corn rolls. And so we've seen a better finish ability and a better finish quality when we reduce the cement with these types of technologies.
Awesome. Hey, Dan, just to let you know, I'm getting a whole bunch of people texting me about how great of a job you're doing. So you got a fan club. I've got about.
Well, it's because I talk too much, guys. That's why. I've got so much good stuff to say that I'm so excited about. And to piggyback on what they said, there's some local contractors around here on the commercial side. I'm not a flat work guy. We pump it. I don't do flat work. I do bridges. So I just put a big machine. It does my finishing for me. But I will say that from an engineering perspective, when you look at some of these larger surface areas and these larger slabs, if you get your steel right, and then you reduce the cement, you've reduced that shrinkage potential. Now, what you can do, in theory, remember we're all theorists here, you can stretch out your control joints and your saw cuts. Now, what that's going to do in the long run is it's going to reduce the owner's maintenance cost, not your maintenance cost, but it's going to reduce the owner's maintenance costs on trying to keep up with joint damage and joint preparation and filling that in. So, and as Joe said with the Chaplin abrasion test, this stuff is hard. And there's another product out there that I played with originally. That's the E5 Catalyst. And man, when you trial that in and work it in, it is hard. So it's ideal for factory floors that see a lot of heavy traffic. That's real smooth and you need running around. And I mean, we were seeing numbers that concrete was harder than anything I'd ever done on a bridge deck. And I consider that pretty good.
Part of that is the way that the colloidal silica creates more of a composite material that we're getting more out of our aggregate. It's not just the paste. And granted, we are making a kick butt paste, an awesome paste, but we're also locking in that aggregate. So when you start seeing that abrasive wear, you get some, I hate to say work hardening, but at least polishing effects from the aggregate instead of there being a weak bond between the aggregate and the paste, and we're just tearing out aggregate. So I got a couple more questions here, Dan. You mind if I jump to those?
You're the boss.
You're the boss. Time is set. What is the impact of time is set from Jay Clark? And Specification Products has some great literature on their website from their 494 that they did. And I believe it's ASTM, what is it, 403 or 408. There is minimal impact on time of set. And I when I say minimal, I want to say 15, 20 minutes, and please forgive my memory, but again, it's minimal. What we do find is that when we're using, and I'm trying to be kind here, those pond ashes or harvested ashes, we did a major project out here 2 summers ago with the United States Air Force, a local ready mix provider, placed 330 yards of concrete with a harvested ash. Again, I apologize if I'm using the wrong nomenclature, pond ash, which caused a huge delay in set times. What we found is by using the right combination of the E5 nanosilica, we were able to bring those time of sets back to where they were traditionally, where the finishers were used to getting on top of the concrete. So that was an added benefit. Another question was from, looks like Robert and Valerie. Have you done any absorption testing? Holy moly guacamole, we have done a whole bunch, and I listed it We've done everything from ASTMC. And when I say we, it's the folks who are working with Colloidal Silica. Joe can speak to it as well as I, but everything from your standard 672 to your wicking test, the German DIN 1048, the ASHTO T259, bulk electrical resistivity. And Joe, correct me if I'm wrong, but I think Professor Luna Liu from Purdue has done some exhaustive testing on permeability and absorption. I don't know if you're still unmuted, Joe. There you go. Sorry about that.
Yes, Dr. Liu has done a multitude of the 1585 tests. That's one test that we've been doing for Indiana Department of Transportation for their validation.
And for those of you who don't know what that test is, it's a capillary absorption test, and you're taking like a 4-inch diameter puck that's 2 inches tall. You're sealing every side except for the flat surface that's going to be facing the water. You put in 3 millimeters of water. It's a 7-day test where you're measuring, it's basically a mass gain, and it translates back to this capillary intake because you're going against the force of gravity. You kind of draw this water in based on the pore sizes and the connection between pores, the pore connectivity. So yeah, there has been some exhaustive testing on permeability, not just on the macroscopic scale, but I think Professor Liu also did some work on the microscopic scale, Joe, looking at, you know, the E5 nanosilica and the cement paste and the permeability from there. Is that correct? Oh, I muted you again. I'm sorry.
Yes, we're actually taking it a couple steps further. Dr. Liu is moved into CT scanning, and we are starting mercury intrusion next month.
Oh, that mercury intrusion porosity. I flipping love that stuff. So we had another question from Jaden. How has the feedback from engineer in terms of acceptance and moving away from the traditional wet cure? Dan, do you want to take this one on?
Yes, I worked with a local firm. I can say that they're my favorite because I just love them, but it's Engineering Resources out of Fort Wayne, and they've got a lot of SEs, and I mean, they're brilliant. And one of them in particular is Kurt Heidenreich. And he is, I will call a bridge god in quotations. He's the man when it comes down to it. And he was the engineer of record for those Whitley County structures that I did. And Joe and I went in and talked to him, and and Joe can back me up on this. We left and Joe goes, man, he asked me questions that nobody else has ever asked me. And it's things like that that really give you the confidence that he's looked at everything, and we've done the jobs henceforth and so on. And you know, one of the things Kurt said is, "Where's this been for 25 years? You know, this is amazing." So that's a group of structural engineers in both vertical and horizontal construction that love it. And they are all about, and what most engineers, believe it or not, in the consulting world, they think that if they can make it easier for the contractor, they will get a better product when it's all said and done. They'll find less abuse. The more you hold a contractor to very specific, tight specifications, the more they're uneasy about their methods, and the more mishaps happen. So when you can do something like this, and I think somebody had mentioned something about set time, and what I really liked about internal cure and what I noticed, and this flows right into the wet cure, is that in a bridge deck, when you start pouring, like I said, it's narrow and long. So all of your loads of concrete you can see in plain lines. In the old days, I say the old days because anymore I can't tell the difference. So you would see a wet load or a dry load next to a wet load. Now, if I'm a flat work guy, those are all different times for me for when I can get on that concrete. But you could see that based on the bleed rate. You could see the wet and dry loads and how it tined. With the addition of the internal cure mechanism and the liquid fly ash, I can't tell you where those phase lines are. It really takes a lot of the inconsistencies of batching out for us guys in the field. So when it comes out of the truck, on a normal day, right? You've got all kinds of things in batching. You've got your holdout for fine aggregate moisture and coarse aggregate moisture, and it changes through the day. Certain drivers then go wash up, and they've got hold water back there from their wash water. So some wash a little better, some don't wash as well. They've got leftover water in their drum on their second way around. So all of that goes to what you get coming out of the ready mix truck. And when we started implementing the internal cure and the liquid fly ash, it's amazing how consistent the concrete acted and the way it looked. That was what was important for me. That's what I've seen the flat work guys go through, is once they start and once they start placing, and then for the delay for their finishers to get on it, they can start right where the placing crew started and work along the same line. And it looks like an assembly line for concrete. Whereas before that, the finishers themselves riding trowels would have to know, okay, well, this is a little too wet. This needs to be hit right now. I got to jump ahead and hit that because it was a dry load. Well, that's pretty hard to do. But what I like is the consistency. Like I said, if you can make it easier for the guys in the field to place it and finish it. And I think that was Joe's main motivation, is he was a finisher and he was tired of getting inconsistencies. Right. And when he started looking at this stuff, man, I saw it in the first Bridgeport. It's like, I can't tell where the last load was. I know in my mind mathematically where it should be, 3 or 4 feet, along that bridge should be 10 yards of concrete. There's a load. But when you start looking at things and looking at it over the long term, and you can't see that phase line, something good is happening there. Something good is happening to uniformity and consistency.
And I just want to say something about that. We were working with the ready mix provider this summer, and one of the issues that they were having, they could not consistently get their slump in airs. If their air was at 7%, the slump, which was supposed to be a 4 to a 6, was at an 8. And if the air was at a 2%, the slump was at a 3-inch. And no matter they put air, they loaded in the back of the truck, or they added it at the mix or at the center plant mixer, we just couldn't get control of the mix. Using the LFA, we got a handle on it. We didn't have any single rejected loads, and not a single load needed to be adjusted on the job site. Now that right there, I know that's not something that we can measure directly, but it's a lot easier to keep the job going where we don't have to worry about metering in and dialing in our trucks either at the shack or at the job site or rejecting loads.
Oh, to concrete, it's of imminent importance. I've got a pretty thankless job. If I've done a bridge perfect, nobody even knows they drove over a bridge because there's no bump. So it's the same thing for us contractors in the field. When everything is going smooth, we don't even stop to thank Ready Mix that everything's going right. But we sure know when it's going wrong. But I think that's okay. When you're doing your job well from the Ready Mix producer side, nobody's yelling and nobody's complaining. It just goes, and the job works like a machine. And that's what you're going for, everybody being happy.
It's similar to, having dinner with your kids. If everybody's quiet and eating, there's no problems. Right? And I'm not comparing ready mix providers or contractors to kids. That's not what I was doing.
I just compared colloidal silicas to beer, and I'm a contractor, so you might be right there.
So Jay Clark asks, is there anything new coming out? Yes, there is some amazing new, awesome, flipping, cool as hell research coming out. I've already had one person let the cat out of the bag today. Spoilers happened, and I promised I would not let that happen again. But I think I'm allowed to give a little bit of a hint. So something that is not new is that we have known for a very long time that using E5 nanosilica will increase the concrete's resiliency to de-icing salt attack. Jason Weiss created a beautiful set of work, and I believe it was the support of a lot of DOTs, but I think it was primarily out of the Indiana DOT. So we took advantage of the system that he created and found out some awesome stuff, and we are going to be publishing that shortly. But ultimately goes back to understanding why nanosilica is such a champion when increasing the resiliency to de-icing salt and de-icing brine attacks. So that's one of the newer things coming in, but I don't want to spoil the outcome because it's just really, really cool. So look forward to that from the Transportation Review Board. We'll be sending out that link once it gets published. And let's see, any other questions? We are coming up to the end of this presentation or this panel discussion. If for some reason I missed any of your questions, we'll be sure to email you and answer the questions. Don't forget to get Patchouli your email address. We'll be giving out t-shirts to everybody that was on today's panel discussion, and it's our first cut of our t-shirts. This is actually coming as a surprise to Patchouli. But for now, I unfortunately have to cut this short. We've got whiteout conditions over here, and I've got to go pick up the kids from school. But I want to thank everybody for joining us today. This has been an absolutely amazing discussion. We got a lot of great questions that we're going to be putting together, saving, and sharing with the group. I'll be sure to share my email address with everybody. Please do not hesitate to reach out and ask me any questions related to concrete and colloidal silica. And with that, I'd like to thank Dan and Patchouli, as well as the rest of the folks at Colloidal Silica for Concrete for putting this on. Y'all are absolutely amazing. So thanks again. Go concrete, beat asphalt.